Yeah, we see it.
Waiting for it. Yep.
Stiffying. Bro, I'm
Now,
stiffying right
remember,
now.
Rob, you can have your priority push to talk set up, and
Oh,
in this channel, you can just mute people if they're obnoxious.
I'm too dumb for this. I'm finna head out.
I have it
So,
ready whenever you are.
so like, what's the priority thing?
It's just a setting in Discord for push to talk. But you can just go off voice activity if you want.
Okay. I guess I'm mad. Or you can call me Rob. It's whatever. And I was asked to chat about particle physics today. So that's what I'm going to chat about. And I think the way I'll do this is I have quite a bit of slides, but we can kind of have this be like a Q&A a little bit. So I'll talk about things, and if you guys have questions, just feel free. Um, so let me click in here. Let's talk a little bit about my experience and why I'm kind of qualified to talk about this kind of thing. So I have, how many years is it now? Nearly 6 years of particle physics experience now, doing like research stuff, lab stuff, all kinds of stuff. So I'm a PhD student right now. In my undergrad, I did atomic physics for about 4 years. I got these pictures of pieces of accelerator that I worked with. I can turn my volume down. Hold on.
No, that was my end stuff.
Oh, okay.
You're good.
Okay. Okay. And so the kind of thing we did here is we ionized atoms. We just stripped them of electrons with this ion source. And then we shot them down a beamline at rather low energy, mind you. And then we hit it against like either a foil or later on I did like this a radiation experiment with solar panels. And so we did that. I also did some calculation theory stuff, but that's mostly what my undergrad was. Let's talk about what I do now. So right now, I'm not quite directly part of CERN yet as part of the one of the collaborations, but I work with people at CERN. It's a little complicated the way joining the collaboration works. I have to get like a certain amount of hours as part of the experiment to be officially part of like the author list. But right now, I'm working in high energy physics. Been on analysis for almost like a year and a half now. My first analysis as part of my PhD is almost done now, but it's not quite at the point where I can talk publicly about it. But I can talk more detail about the kind of stuff that we do indirectly. But basically, what we do, and I put like a little red arrow to kind of signify the experiment I'm part on, CMS, is we look for new physics. So a good example of that is there's been the search for dark matter or like a quantum gravity theory for what 40 to 50 years on both of those for now. But there's other things which I'll talk about later in more detail. I think it's about time I grief you. No, not yet. Okay, so what was I planning to squeeze in the hour? Finally, all these topics. I was going to talk about what do we mean when we say particles in particle physics, and I want to talk about like all the like popular like pop science concepts and why people might be wrong about some of them. But anyways, we're going to talk about what particles are, what it means to be quantum, as well as the flaws of Schrodinger's cat and double slit experiment. And I'll talk about the more frontier topics like quantum field theory, what the hell's a virtual particle, and we'll talk about dark matter and stuff like that. And then maybe I'll try and figure out something to fill in some extra time since Sarge is out. But yeah, this is roughly the idea. And so there's going to be a lot of related concepts to these. It's time to grief yet? Here we go. So, the good news is, the goal of this talk is not to make you understand this hideous equation.
What fucking cursed Latin is that?
That looks like it summons demons.
I hate math.
So, yeah, so there's going to be... I'm going to show equations in my slides, but the goal is not for you to understand, like, everything about them. It's just, like, to have something to guide us along. So what you're looking at here, basically all these letters, for the most part, they're either couplings or fields. And this is the equation, it's called Lagrangian, for the standard model. It basically dictates and describes how all of the forces we can describe the standard model and all the fields and particles work and interact with each other. Which, in this case, that would be the strong force, the weak force, the electromagnetism, and not gravity, because we don't have a working model for quantum gravity. Maybe I'll talk a little bit about that as like a post thing. But I just wanted to grief you guys with the expanded form. We'll talk in more detail about some things. But yeah. So here's a little joke. What's a particle? Well, it's the kind of thing we've been going at for a very long time. I mean, surely there was probably this kind of conversation way back. We can talk about Democritus thinking that, all things are made of smaller things, and like the whole concept of atomos. So that really does take you back. What do we mean? So when we say particle, we basically mean anything that we could approximate as just like a small point that projects through space and time. So like a good example is, the apple falling on Newton's head. Whether or not that actually happened or not, I don't know. And projectile is something that I'm sure many people who are interested in weapons are very familiar with. As a fun little example, I just put a trebuchet in here because that's a fun example. But yeah, so basically particles are supposed to follow a trajectory, and it's something that we wanted to know in physics, at least in the classical sense. And so, what do we want to do if we want to know how a particle moves? Well, the classic axiomatic way is just to follow Newton's laws, right? And that's something that we teach people when they have like a high school physics class or a intro college class, like engineers, life sciences, all the ropes. They really, that's how they go about learning things. But the funny thing is that's actually not the most fundamental way to go about things, and there's a deeper pattern that just shows up again and again in physics the deeper we go. So for 100 years, we danced around a couple different questions. And so the idea is that, say you have some particle that wants to go from either space point A to space point B, or time point A, time point B. An optimization thing that people kind of wanted to do like back hundreds of years ago, at the very least, probably thousands of years ago. Because I know it at least goes back to like the ancient Egyptians, ancient Greeks. Is how do we minimize or find the minimum distance it takes for object to go from point A to B in either space or time? And so that led us to these concepts of least distance, shortest time. And so like ultimately it was the French who figured out the solution to these problems, ironically. And so the reality is although these looks like they might be like different things, they're not actually. They're the same thing. And they're a reflection of this quantity called action. So the action is just some equation that gives us a number given some path that a particle takes, or any object takes, for that matter. And if we vary that path and set it to 0, that allows us to derive naturally an equation of motion. It just so happens that this concept permeates basically everything. And we'll come back to that in some time. But what the hell does this have to do with, particles in, like, quantum physics? What I really want to talk about in this talk. We'll get there. But let's start with how we even get to quantum physics in the first place. So, although the earliest discovery of a subatomic particle is the electron in the 1800s, I think it's like late 1880s, we didn't have any clue about atomic structure or quantum mechanics just from that discovery alone. And in fact, when we discovered the electron, we didn't actually think about it as a particle per se at that time. We thought about it as rays. The real start of considering this concept of these quantum particles really goes back to the photon. So what I'm showing here on the right is this graph of basically intensity and wavelength. And so basically, what happened near the dawn of the 20th century is that we thought we had almost everything figured out. And we wanted to predict what would happen if you had a box that can absorb and radiate light in all wavelengths. Something much like the sun. What would happen to, like, how much light would come off of it at different wavelengths. And so originally, before we observed this idea of quantum, we thought that it would just go off for infinity as wavelengths got shorter and shorter and shorter. But we quickly found out that is not the case. It follows this, what we now call the Planck radiation formula, or the Maxwell-Boltzmann distribution. And basically, what this means, in order for us to make light do this, or at least model light in a way that does this, is that we can only allow it to oscillate at allowed frequencies. And that's what we mean when we say something's quantized. It can only be at specific values, rather than a continuum. And from there, everything just kind of started going crazy. From there we observed atoms, and then all the models of atoms became a thing. Like here I got an example of the Rutherford gold foil experiment, where we really observe quantum scattering for the first time, which will be very, very important in these later slides. But I think before getting into anything, there's one experiment that not a lot of people know about, but is really, really important in illustrating all the important things in quantum mechanics. And that's the Stern-Gerlach experiment. It happened quite a bit later, but it's really foundational in just illustrating everything. So the concept is, and I have this picture here to try and help us visualize what's happening. Oh?
Your stream's still up.
Yeah,
Oh, okay.
You're fine.
No,
I was confused.
fine.
Hold on.
I had something extra going.
Okay. So basically, what happens is we prepare a source of say silver atoms. There's a reason for that, and I can talk about it again later. But anyways, we have a bunch of silver atoms. They have a bunch of electrons that orbit them, and you set them in a furnace, which allows us to ionize them. Much like what I did in my undergrad. And then you pass these atoms along a beam and have them pass through this uneven magnetic field. So it allows them to come out with one of two different kinds of spins, basically. Spin up or spin down in some direction. Like XYZ or something. So classically, like if we're just doing things with no quantum, we would expect that if they hit a sheet, say like release light off of it, we'd expect it to just be a smooth line, a continuous line. That's not what we observed. What we observe is that we see two spots. We see a spot that has the up and a spot that has the down. Nothing else. There's no other magnetic alignment. So what we find is that this too is quantized, which is a evidence of the quantum nature of electrons bound to atoms. So quantization is the first thing we learned about that. The second thing that this teaches us is that there's uncertainty. And by uncertainty, I mean the classical Heisenberg uncertainty principle. Normally we just call it the delta x, delta p, greater than or equal to h bar, which that h is the same h in the energy equation for light. But anyways, similar thing here. If you want to measure a different axis for the spin, you can only know so much about each axis, basically. And a good show of that is that you can do sequential Stern-Gerlach experiments. So you can just add another uneven magnetic field in another direction, and you can see that you can't measure both like X and Y to complete certainty. But there's another thing that will happen if you have enough magnetic field regions, and that is if you continue to do this experiment at different stages, the information you had at the first one will no longer be preserved. So if you have, say, the magnetic field aligned with along the X, then along the Y, so that no X is allowed through anymore, and then back along the X, any information from the first step of the experiment will be gone, and you can still end up with an X-aligned spin at the very end, which is very weird. It's actually one of the things that really confuses people about quantum mechanics, but it's a consequence of how it works, which I will get to shortly. So basically, experiments like this and others tell us all kinds of properties about the particles that we call quantum exhibit. And a bunch of smart guys, some of you may know their names, found what math they satisfy. And by these people I mean like Schrodinger, Dirac, and Heisenberg, people like that. They satisfy linear algebra, which is just advanced algebra with some extra concepts. Specifically, they're described by vectors that are complex, and by that I mean vectors that involve components of imaginary numbers. That entire concept is the reason why we find out that things have uncertainty, that information destruction is a thing, and all the crazy shit that happens in quantum mechanics is a consequence of that. But before we go any further, I want to address the big elephant in the room that this introduces. So let's talk a very tiny bit about philosophy of physics. So classically, like going back to Newton, Galileo, that kind of stuff, physics is deterministic, right? So if you throw a ball, you can predict where that ball is going to stop exactly, just about. But quantum mechanics, because of having these complex vectors, introduces uncertainty. And then this comes to this concept of wave function collapse, which I'll talk about here in a bit when we talk about double slit. And so, because of this, you have to have an interpretation of quantum mechanics. And there's a lot of them that are popular. And so, the most popular one is the idea that quantum mechanics is just probabilistic. So, what that basically means is that if you produce identical systems to your initial like thing you want to measure in quantum mechanics, that you'll have a statistical likelihood of seeing something or process that you want to see happen. And that one's very useful. We can do a lot of science with that. We've made all our greatest predictions doing that. The second one, which is very popular in pop media, pop science, that kind of thing, is the many worlds interpretation, or the Everett Wheeler idea. And basically the idea that whenever you measure something, every possibility that could happen happens in another quote-unquote world. But the issue with that is that there's no true observable. We can't predict anything using this, so it's no longer physics or science at all for that matter. So, for the most part, it's basically like a abandoned idea in actual science. But it does make for some fun media. Then there was Einstein's concept of hidden variables. So the hope was that it's not that the states are complex vectors or anything, but there's something hidden that we don't know. Unfortunately, we've effectively proven this idea to be wrong. And maybe if I have time, I could talk a little bit more about that, like as a post topic. I don't know. But the shtick is that for measurements we've done, we've basically proven that there are no hidden variables and that state vectors tell us everything there is to know about a particle. There's yet another, but we'll get there later. So let's talk about Schrodinger's cat. As like the first major big topic that people get confused about. And to not clear up confusion, I'm actually going to show you like a picture that really shows you all the real elements of this thought experiment. So basically the idea is that yes, there's a cat in the box that maybe you're alive or dead when you open the box, right? Except there's a lot more going on that makes this probabilistic, like I was alluding to. So you may notice that there is this black vial in here. And the vial is supposed to be a vial of poison. And then we have a hammer attached to the side of the wall of the box that is tied to a radioactive source. So basically, there's a random chance that that radioactive source is going to emit radiation that's going to hit the hammer enough times to break the glass. So there really is a truly random chance that you open the box and the cat is dead. But ultimately, the goal of Schrodinger's cat is just a thought experiment to illustrate what leads Schrodinger to his equation. And so, like, an important thing is we have multiple observables, like what's happening with the radioactive isotope atoms or nuclei, whatever you choose. The state of the poison, state of the cat. These all have the same features I mentioned before. They have uncertainty, information non-conservation, they're quantized, and it's all probabilistic. And by that I mean we have these states and they're normalized. That's basically the concept, which leads us to Schrodinger's equation, another math equation that people are not guaranteed to understand. The only thing I really wanted to say here is that given some state we call psi, Schrodinger equation allows us to evaluate what we call the time evolution of that state. That's just a fancy way of saying the Schrodinger equation allows us to predict what's going to happen to some particle at some time. Not to 100% certainty, of course, but we can predict something about the state. That's basically the concept. So now I want to talk about the double slit experiment, okay? This perhaps is the more contentious of most of the topics that I'm going to talk about. So the idea of double slit experiment, for those who are uninitiated, is that say you have some beam of particles that you can shoot through two slits. In this case, we were looking at like electrons. You can do the same thing with photons. So the idea is that if it's a classical particle, we expect it to go through one of two holes. However, that's not always what we observe. And there's two things that come from this that are very commonly quoted in the pop media. The one is, of course, the uncertainty principle, right? You don't know with exact certainty what's going to happen. The other is the wave-particle duality, right? Depending on how this experiment is done, how you detect the particles or how you observe them, they're supposed to exhibit these wave or particle properties. But what if I told you the answer is not both, the answer is neither? I'll explain that here in a couple minutes. So basically, what this is an example of is what we call quantum scattering. So before we do that, I have to explain what regular scattering is. So basically, scattering is what happens when you throw one thing at another thing, and the first thing bounces off of it. Or they both bounce off of each other, if the scatterer is the same size, basically. But anyways, in classical mechanics, you can bounce something off of each other, and you can predict basically exactly what they're going to do. You can't do that in quantum mechanics. Alright, so there's a few things that make it a lot more tricky with quantum mechanics. The first of which is uncertainty. We can't know with exact certainty position, momentum, or energy and time, or any other set of properties. The second that truly complicates things is that every particle of the same kind is identical. So if you were to naively get a bucket filled with electrons, there's no way that you can pick out individual electrons and label them. Every time you measure or detect a particle of that type, you have no idea if it's the same electron or not. So because of that, if you have two incoming, two outgoing particles, when you scatter, you have no idea what's coming in or what's coming out. So when a quantum object scatters, you have no idea what's happening during the scattering. And so what we did as part of trying to understand this is we discovered this equation called propagator. It just some fancy math that happened as part of trying to resolve this funky business with quantum scattering. But this introduces a third problem, which really illustrates something deeply wrong at the heart of quantum mechanics, or just physics in general, because propagator appears in classical electromagnetism too. But the idea is that we see that in the denominator here we have this p squared minus m squared, which means that given the right mass or right momentum, we can get a 1 over 0, which gives us an infinity, which that's a big problem. We can't measure infinities, and if anything goes infinite somewhere, that means we can get things like infinite energy, which is ludicrous. But some really smart mathematicians already invented a way to do this over 100 years before quantum mechanics. And so that's basically by taking this equation and smearing it out to be in the complex plane. That's just a fancy way of saying we're adding a complex component. And I show that here in the right. And I have this little picture of the complex plane where we have a real axis and an imaginary axis. And so basically we contort this integral such that we go around the singularities. And we get rid of the infinities by doing this. The good thing is this allows us to predict things about quantum states. And so we can run calculations and we can make predictions that are very accurate. The problem is that since we smeared out this propagator into the complex plane, it means that it's no longer physical. Once you have those imaginary numbers in the propagator, it becomes a physically undefined quantity. Which means that when something scatters, we don't know what's going to happen. I mean, we can't know what's going to happen just because of the properties of quantum states in the propagator. So this, in fact, does mean that in the double slit experiment, particles are not both waves and particles. They are neither when they're scattering. So that's a fun little idea. So what's this about wave function collapse? So when you observe a particle or some system, you're forcing it to take a stand on some particular state. So that's what we mean when the wave function collapses. These double slit experiments, they showed that. Oh, I already said all this, didn't I? All right. Anyways, let's move on.
This is physics 101. You're gonna double over on accident more than once.
This is some of the most fascinating shit. I love this. This is great.
It's a good morning exercise to wake up to.
Yeah. Of course.
Yeah, doing it up 4 hours of sleep is fun.
Yeah, you've done this
slightly
before.
better than you in that regard.
So, why are things like this? Well, let's take a detour. So, I didn't mention what's the last major interpretation in quantum mechanics, and that's the Feynman interpretation, or path integral formalism, as we call it. So, going back to the idea that what dictates the motion of all things is the path it takes, right? And that's described by an action. So Feynman thought, okay, then what if we could figure out a way to represent the probability of observing something to that concept, the concept of the action? Well, he found a way to do that. And you'll see in this equation on the right that if you remember the form of the action from before, it's right in there. And so what happens is if you take this h value, or h bar, which is just h divided by 2 pi, and you send it to 0, you get regular physics right out of quantum mechanics. Which means that regular physics is already embedded in quantum mechanics. It's just a consequence of when things get too large. So quantum mechanics is actually more fundamental than regular old classical physics. But that's not the end of all of it. It's time to start doing crack. So, let's talk about quantum field theory. So,
Oh boy, I've heard you talk about this before.
I'm about to tell you that although there is a lot right with quantum mechanics, we made a lot of very successful predictions and measurements. There's a lot that's wrong with it. So, namely, the biggest thing is that if you try to make predictions for anything that's going like close to the speed of light, you're fucked. It doesn't work. And there's a few reasons for this. So, quantum field theory is supposed to be basically the solution to this kind of problem. So in quantum field theory, instead of having states of particles, we have fields, and you're measuring field configurations. And we get antimatter as a consequence of doing this. However, the bigger consequence of once we go relativistic is that you can no longer do things in this probabilistic way. Probability is not a thing that's conserved anymore. Instead, the number of particles is, specifically the number of particles and antiparticles, is always constant. So basically what happened is we derived similar things to the Schrödinger equation, but instead for fields. So here I have two of the most popular ones. So on the left we have the Klein-Gordon equation, For the most part, this equation describes force carriers. Things like, say, Higgs boson could probably naively be described this way. Whereas the right side, the right equation, that's the Dirac equation. And that's what describes like electrons, positrons, any lepton, that kind of thing. Any spin 1/2 particle can be described by that equation. And actually, through quantum field theory, any type of particle that satisfies both quantum mechanics and relativity, we already know how to describe. You just have to change masses, couplings, that kind of thing. The problem is that what do we actually measure? Since we've abstracted away quite a bit at this point, right? So the thing we measure in classical physics, or even regular quantum mechanics, is we were able to measure things like position, momentum, and energy of some system or some particle. That, since we have abstracted the fields, though, it's a little more what's going on here, right? So in QFT, we're able to calculate things like cross-sections, which are basically a representation of the probability of observing some process. Like, for example, the probability of seeing a proton scatter off a proton, that kind of thing. Branching ratios, which is, in the context of just high-energy particle physics, is the idea of watching one particle decay into another particle. In regular quantum mechanics, we also had that, but that's just like the probability of one state going into another state. And then there's also lifetimes, which tells us how long those states last. And so we use quantum mechanics, QFT, to make predictions of these quantities. I showed an example of like what a cross-section equation looks like. The most important thing in this equation that is like QFT specific is this m squared thing. That's what we call a scattering amplitude. And that's something that we calculate using these things called Feynman diagrams. So you may have seen these things going around the internet in some places. I don't know. I remember I saw them growing up quite a bit. But basically, at a first glance, they're a nice picture of some scattering process that happens, right? You have 2 electrons that come in, 2 electrons that come out. Well, actually, no. In this case, this is 1 electron, 1 positron go in, 1 electron, 1 positron come out. So this is Baba scattering, I think. But, oh no, it's Compton. But anyways, this is very similar to that picture I showed before, except I've unobscured the center, basically. But the reality is that this is not just a picture, but each line and vertex in this is just a representation of math. And so, and actually, in this case, the lines have additional factors because they have electrons. But it's just a mathematical model. So this begs the question, what are virtual particles, right? So if we go back, let me see if I can go back. If we go back to this picture, right? We have our incoming particles and we have our outgoing particles. And we have this particle in the middle, which is just a photon. So in this case, we normally call this an exchange particle or a force carrier. But what really is that, right? This is actually something that a lot of people stumble on. And people like who've been in the field far longer than me struggle with this, I've noticed. And that is that people talk about this, these exchange or virtual particles as if they're real physical things that are measurable, and they're not. The whole like concept of virtual particles is that they aren't observable, right? But the reality is that they're not something that exists in the first place. People for years used the idea of uncertainty to try and excuse that they could exist, right? Like you do like a delta E times delta T greater than or equal to h bar. But that's really not what's going on in these Feynman diagrams and in these actual processes in real life, really. Really, anytime you have these internal lines or these loops, which I have like some like little pictures for examples, that's just a collection of propagators mathematically. It doesn't represent any real particle. It's just math. That's it. So let's talk about another concept that's a little fun that really flips a lot of things on their head. Something that I only really recently came to terms with myself. That is that are things in science that we call laws truly immutable? How can we be so sure that we're right about things? Well, the truth of the matter is we can't. The scientific method can only definitively prove theories, models, whatever, wrong. We can't objectively prove something that is right. There are things we call law, but I'll show you that things aren't airtight. I'll go over a couple examples to illustrate this. Starting, unfortunately, with a more complicated one. So, it's all fine and dandy that in QFT we could predict something with no loops, what we call a tree level, basically the first term in a series expansion. It's basically just the first term in our approximation. But the moment we start introducing corrections to that, going to the higher order terms, we start getting infinities. And that's where our concept of things no longer being as definite as we believe them to be starts to go away. So this is about the good time for me to explain this concept of action in a little more detail. So the Lagrangian is this quantity that we had in the action before, and it's also the equation that we use to describe how particles interact in the standard model, or any object behaves in general. It's basically this concept that's much like, say, total energy. It has the same exact units. We just manipulate it a little bit. In classical physics, it's just the quantity kinetic energy minus potential energy. In particle physics, that's not too different in reality. It's just kinetic term minus mass term. Plus interactions, but that's about it. But the way these work in particle physics is that we write this quantity in terms of fields, which is things like this A and psi symbol. And then we have couplings, things like E, which is just like charge. And so when you have an interaction, it's coupled together by different fields. But there's a bigger idea here, and that is going all the way back to when we first started describing nature using the concept of this Lagrangian. Everyone really thought this was a holy equation. And actually, a kind of scary thing is that Dirac, in his later years, he just kind of like gave up on QFT, and because he believed this quantity to be sacred, that there was no getting around it, that it was the definite equation. But the reality is, it really isn't. Because of the fact that these aren't the things that we measure. We don't measure the absolute value of a field or its couplings. These are abstract things that do allow us to get quantities, at least at the tree level. However, a way that we found a way to get around these infinities is that instead of writing this Lagrangian in terms of the bare values of these fields, these couplings, we write it in terms of our observables, our cross-sections, our lifetimes, or what have you. And when you do that and let these couplings, these fields move, then we can actually make predictions that are obscenely precise. That's actually what allows us to make the standard model what it is. And it's what led us to the situation we have now where the standard model is the most accurate model of anything we have out there. So the consequence, the Lagrangian is no longer absolute or holy, but we have a very useful model. But this isn't only true of quantum mechanics. All models have limits. And to really illustrate this, let's go back to a very simple example. So say you have a rope, and you whip the rope up and down so that you're seeing the peaks and the troughs as it's a wave, right? I'm sure this is an example that some people had when they were in high school, or it's something that happens when we have an intro physics class in college. So what someone might do as part of like an upper level undergrad course is you could model this rope as like a bunch of individually oscillating segments that go up and down. And that's basically what this equation is doing. It's just modeling it as a bunch of harmonic oscillators. But this model has the exact same problems that we had when we did QFT. That if you go to the limits of this, say if you have arbitrarily small distance or mass, things start going to infinity. So what do? You redefine the model in terms of observables, and you introduce a cutoff, and then you can make your predictions and go about your life. The point of this, though, is to illustrate that everything has limits. We can't arbitrarily, which by that I mean know the infinite accuracy, anything. Another good example of things that we can't know the infinite accuracy is zeros, right? So like a prediction that we have from the standard model and classical electromagnetism is that this concept of the photon has to be some object that doesn't have a mass. So mass equals 0. But that's not something you can prove. You can't prove 0. And that's actually like a fun thing that's been going on for like well over 100 years is that every few years, it's been getting longer and longer now because it's getting harder and harder to set limits. People set further and further limits on what the mass of a photon may be. We never can know with complete certainty that it's 0 because every detector one would have has a limit to how certain it can be. And so let's start talking about these fringe topics, right? So the standard model is great, quantum mechanics is great, but there's many questions that it doesn't solve, or at least we have no solution for at present. One of the big ones is this concept of matter-antimatter symmetry. So if one is to believe that the Big Bang is a thing, then one would rationally believe that there was an equal amount of matter and antimatter at the very beginning, yet there really isn't right now. So what the hell is on with that? What about gravity? Is there a quantum model of gravity? Not everyone's convinced. Some are. Where is supersymmetry? We've been trying to observe whether or not particles have these heavier partners for, I think, like 30 years now. We don't have any direct evidence of supersymmetry, but we do have indirect evidence. And that would be that the Higgs boson has the mass it does. We had one chance in all of our efforts to completely disprove supersymmetry. But the fact that we observed the Higgs boson and observed it at the mass we did means that supersymmetry is on the table and we can't completely rule it out right now. Which leads to another topic. Why do things have the masses they do? All right, the Higgs boson is much lighter than it should be for reasons that we don't fully understand. And in fact, for whatever reason, it couples obscenely strongly with a top quark, and no one really knows why. Because the top quark is more massive than the Higgs boson is, and that's a fun question. Neutrino oscillation's another fun one, although a little bit outside my field of expertise. Next,
Huh.
Yeah, he died.
that's the idea that we have at least. Oh, I hear.
You died for a couple seconds.
Yeah, I noticed my connection was going down for whatever reason. My internet sometimes a little weird.
Campus internet be like.
I'm not even on campus. I haven't been on campus all week, except for like Monday, when I had great exams. Neutrino oscillation is just the idea that given these three flavors of neutrino associated with each generation of electron, they can oscillate between their flavors while they propagate. I know a few people who are involved in trying to measure these things. There's more stuff related with neutrinos that are big questions too, like what masses do they have? Are they massless? Are they their own antiparticle? We don't know. And then of course there's the big question that everyone's been wondering for a long time now is, what the hell is dark matter? Which I'll clear that up a little bit. So, a long while ago, back in the 1900s, like 1950s, 1960s, we expected to observe galaxies that have rotation that depends on its the radius from the galactic center. And that's what like this dashed line shows in this plot, right? But when you actually observe the rotation velocity at different distance from the galactic center of galaxies, you find that it's like a flat curve, which completely flies in the face of what anyone would expect. And so we just alleviated this. Well, I say we. I mean the astronomers, the astrophysicists, alleviated this by adding an extra term to predictions, and we called it dark matter. And so this topic has evolved quite a lot now. So we've been in search of this thing called dark matter. We have solid reasons to believe that it may be a particle, but there's nothing really for sure that tells us that that's the fact. But cosmologists are rather convinced. They've done a lot of fun little predictions based off of taking the Big Bang Theory to be true. And so that allows us to set limits on like how much mass comes from matter, antimatter, and dark matter. And so for a long time now, we've been doing these particle searches looking for dark matter. I've been hearing about a lot of different ones in recent times, past couple of years. In general, we call this the dark sector. Some people call it the hidden sector. It's just basically something that it's hard for us to observe. And in the particle physics sense, the way we define dark matter is it's something that doesn't interact strongly with anything else in a standard model, which is the reason why we haven't observed it yet. So like one such, and that's the reason why we call it the hidden sector, dark sector, that kind of thing. One fun model I heard of is the concept of dark atoms. So that's just the idea. It's part of like this whole group of ideas. There's also like the dark standard model, that kind of thing. That instead of there just being like one dark matter particle, there's several, and not only are there dark matter particles, there are dark matter bound states, so they can form dark atoms. One fun astrophysics idea I saw a talk on was something about the concept of if there are dark atoms, then they can accumulate on the surface of moving stars because of the warping of space-time. So one could possibly observe them indirectly doing that, measuring the motion and emissions of a moving star. I've heard some interesting experiments talking about dark photons. So there's a experiment, I think it's called Light Through a Box, that some collection of National Labs is working on. Basically the idea that there is like some way to couple dark photons to, which is just a dark matter photon, to regular standard model photons so that it could pass through a box in some such way that we can measure. Some sort of Higgs interactions we call the Higgs portal. That's actually a little closer to what I work on. So one could assume that if there is a Higgs for regular matter, what if the Higgs interacts either the Higgs interacts with dark matter, or what if there is a dark matter version of the Higgs? So those are things that we look for. That's kind of a project I'm on right now. Some people think that dark matter might be another kind of neutrino called the sterile neutrino, which is much more massive than the regular neutrinos. And then the mass regions that we expect these things to be. For a long time, we expected them to be massive particles, but we spent a long time on that, and so now people are trying to push down into the lower mass region. But there's a lot of stuff on that. If I really spent a lot of time trying to think about all the stuff I've heard about this topic, I'd be here for quite a while, but I don't remember all off the top of my head.
What I know is that there's always something smaller.
No, do I? Oh, I think that's the last slide I had.
Well,
knowledge.
It sounds like you played your time very, very well to the initial 1 hour.
I mean, this is not the first time you've ever done a presentation, and you're not doing it at such a stiff crowd with the professors.
I'm quite willing to learn just about anything in any sort of way. It sounds like Sarge will be like 15 minutes, actually, late. So, Rob, what do you got for 15 minutes?
So,
I don't know.
Property.
So
maybe ask you some questions, and then we can just go do it back and forth.
We got Meister. He seems.
Okay, yes. Hello. I wanted to wait till you were done with your presentation to pop in. That was fascinating.
Thank you.
I'm trying to think of where to even start. So I guess the biggest thing, just to kind of hop right into a statement, just to kind of start a dialogue, is I'm just so interested in the fact that, right, you actually work in a field of research that is actually pushing the boundary of our understanding of the universe that we live in. I work in a very established field, so it's fairly well known, electrical things. So, right, there's not a whole lot of boundary pushing other than application of existing technology. So the fact that you're working with stuff where, right, you're not talking about laws and known factors, you're sitting here and pontificating about what could be, and that's actually how the boundary is being pushed, right? There are theories as to how these things may exist, and we don't even know. So that's just fucking crazy.
Yeah, it's a fun thing, right? Because especially for people who have only done high school or have done a bachelor's, you're taught things at various levels, and then you're even taught in such a way that you believe things to be definite, to be laws. And when you learn that that's actually not true, it kind of boggles the mind a bit. And it kind of led me to understand something a little weird about how education works. So the way I've ultimately come to terms with it is that really what we do, starting from some of us have pre-education. I had a pre-K I went to when I was younger. But at every level of education, basically what happens is we're told lies that resemble the truth more and more until you're ready for the truth the higher you go up. And
yeah,
so
that's a pretty good way to put it.
It's fascinating because of the fact that people who did not pursue that any further hold what they were taught as the absolute. And so it leads to fun little misconceptions that permeate wildfire.
Oh yeah, right. And you end up with people that go into their respective fields with this absolute monolithic knowledge of this is the way things are. And then if something challenges that, they they don't know how to react to it. What do you
Like
mean
string
that
theory.
what do you mean that what I know is wrong?
What do you mean I got given a half-truth when I was 6 years old and got reinforced that for another 5 years?
Well,
What do you-
or what do you mean this concept that I've been applying my entire career is actually incorrect when you operate outside of the narrow scope that I use it in, that it's actually valid?
What do you mean Newton wasn't 100% correct in the 18th century?
What do you mean Ohm's law has problems?
Ohm's law is a fun concept, actually.
Oh, okay. I mentioned that
Right
I'm
in front of the
electrical.
beast.
I was gonna say yes. I am an electrical engineer, and I work in a field where Ohm's law regularly is kind of. You would be better off applying Maxwell's equations, and a lot of the people I work with don't like that. Right. The concept that electrons actually travel as a wave and not as little particles along a piece of copper boggles the mind of some of these engineers who have been there for 30 years.
The funny thing is that's not even the correct statement either.
Oh, please go on. I'm on. Okay, no, yes, please explain.
The electron doesn't move in a conductor. It's the energy density of the electron field moves.
Yes, right, yeah, yes, it is the propagation of the wave front that is generated by the electron hole in pair, basically.
Yep.
Yes.
I'm
Okay.
working in a field where shit goes downhill, and don't look at too much for the key rules that I have to live with.
And you know what? That's important because if our shit didn't go downhill, it would pile up in our homes.
Yeah. We'd be like London until 50 years ago. I get into trigonometry, okay? I do that.
This is an open invitation for any UKers to come in and fight us, so.
Yeah. Well, they know that I'm right, so they can't fight me on this.
The thing I've noticed that's kind of funny, so I'm an experiment guy. I'm friends with theorists, but a thing I've noticed about other experiment people in my field is that once they get done taking their classes, they do their PhD. Just like most other people, a lot of the advanced knowledge just falls out the back of their head. I've legit been at places. I've been at labs where they're giving a tour talking about some complex. I think the more recent one is I got to see the muon G -2 experiment over at Fermilab. And the guy giving the tour started talking about these virtual off-shell particles as if they were real things, and I'm like, buddy. But it's okay. I get that people don't get this by default, and if you don't really try to get it, then yeah, things are going to not connect right.
Well, and that's why this. I mean, right, to put it one way, from a more layperson's perspective, this sounds like magic, or this sounds like bullshit. Right? It's so unintuitive. It's so esoteric, unintuitive. It doesn't make sense with the way that you can interpret the observable world using your basic senses. That people are just like, what the fuck are you talking about?
The fun thing, though, is that in a way it's better than magic because we can actually predict what's going to happen.
I would make a joke about RF, but this stuff goes way beyond RF.
The bigger problem is that on the low energy condensed matter side of things, and even the statistical physics, is that for decades there was a lot of flimsy models that just flew around for years, and they work to an extent. Don't get me wrong, but they're definitely not factually correct with what's actually happening.
When you say flew around, does that mean physically thrown into an airplane, or just this is something that you can use?
Something that you can use. But a good example, in condensed matter, I would say is the Drude model was prevalent for years. just a model of conduction as like a gas of electrons, like an idle gas, and that's just not how a quantum gas works. But I mean, we got some decent results out of doing it until you measure heat capacity.
It's always thermodynamics that fucking gets you.
Honestly, thermodynamics is one of the hardest subjects. Like when you get down to it,
I have never had to take a formal thermodynamics class, and every time I try to engage with it, I am very careful to not overstep my bounds because I fall down rabbit holes so fast, and it's like I don't know what I'm talking about. I need to stop.
Is one of the few laws that are as close to being absolute as possible. I think, like, it is of the most absolute.
it's absolute within the definition of your system.
Yeah.
Which that's in its way proving the point I was already pointing out, which is that there are always bounds to your definition of law. You just have to choose them in an intelligent way.
Yeah. Well, right. That's why coming up with a unified theory of everything is almost a fool's errand, because you can't possibly define a scope of everything.
Yeah, remember, if anyone ever tells you they have a grand unified theory, they're probably smoking dope.
Exactly.
I tell you, it's really
So they
funny
have
getting.
that in common with those blue collar guys, eh?
It's really funny getting the emails in my spam folder from X guy who finally figured it all out, mass emailing our entire department.
Yeah.
The only perpetual motion machine I see is your fucking mouth.
Remember, the hardest
No,
part
really.
of perpetual motion is hiding the batteries.
I think the funniest thing I've learned since like actually talking to people in the field a lot recently is that the dealing with the conspiracy nut thing has been a thing for at least 50 years.
Yeah.
Since the phrase was popularized by the CIA.
So when you say that you get, so I guess just to kind of poke at that a little bit, you say that you get people emailing around saying they've come up with like, a grand unified theory of everything or whatever. Do you actually get people that somehow get your email or your department's email and are like just emailing you crackpot theories every once in a while?
Absolutely. I'll actually see if I can dig one up.
Yeah, absolutely. I would be very curious to hear, right, what's the funniest one that's gotten passed around, right? The one that's like, oh my god, everybody take a look at this.
I think the funniest one is probably there was some like group of spam emailers that try emailing suggesting that the axis the Earth rotates on is a physical axis.
What?
The globe model is absolute, as in there is literally
There
a
is
rod through the middle of the
skewer
Earth.
going through the center of the planet to hold us in place.
No, really. There was like a group of emails I got about that. Actually, like several people that I know got it.
Listen,
Shish kebab Earth
the
theory.
most accurate, the most accurate model I think I've seen. The best way I can describe it is that the orbits of the planets around the sun make a cone that are close to the sun as it is, well, closer, I guess. As it's closer in diameter, it's closer in distance. I'm gonna say on the vertical. Vertical doesn't make sense, but you know what I mean. As one dimension is closer, so is the other.
Yeah, I don't know if I still have these anymore. I think like the spam filter must have deleted them or something.
Damn.
All good. I was just curious.
Starman says, obviously, that's what my globe has.
He figured it out.
Yeah, I think the most common one I've been getting lately is people trying to suggest that all forces are just electromagnetism. But that did not work.
Waves, man.
The moment you try to apply the strong force as electromagnetism, everything will fall the fuck apart.
Yeah. No,
Clearly, because this is my highest level of understanding, this must be the truth.
Yes. No, if people are like everything's a wave, man. Which I mean, it's usually potheads to say that. which that's not true, but a lot of our non-touch perceptions rely on the same waves, like hertz ranges. Your sight and hearing, to my understanding, are on the same scale. They're just different sections of the scale.
Yeah, the whole we're all just waves, man. We're all part of a larger entangled system. People who think that doing DMT once gives them all knowledge of quantum mechanics.
No, our sight and sound perception are waves. Everything else is very physical.
Well, and all right, and
hardcore.
this is a bit of my I have a hammer, everything looks like a nail way of understanding things, but at least from an easier to grasp angle, thinking about a lot of that stuff as waves isn't that incorrect. At least at a higher level.
It's not incorrect, but it's not correct in the way most people mean it.
Yes, exactly. Right. Again, if you dig too deep, all laws are probably incorrect to some degree. It's just at a macro scale, this is where I'll have to puff out my chest and say, on an applied level, they are laws. They're very practical. They're functional. On an absolute level, no, they're probably wrong. Right. Like Ohm's law. On a practical application, Ohm's law is very correct. On a microscopic, if you really dig down into it, Ohm's law has problems.
Yeah, overall, I think the funny thing about classical mechanics is that anything that has to deal with something that is of the scale of us personally, we have perfectly described.
Yeah.
But once we exit our wheelhouse, we're lost.
Yeah, exactly. That's right. That's where I go from the at least for our current level of technology on the practical level, on the macro scale, they're correct. They're very useful. But then when you start to drill down, once you exit our technological understanding and you start to push that boundary, that's where you get into problems.
It's actually what makes one of the foundational axioms of quantum mechanics really interesting is the fact that yes, it's something completely outside the range of our senses and our logic. We did still discover that everything about a quantum state is complete. It gives us complete information about the system or whatever particle in that state that we want. And that's counter to the whole thing about hidden variables. But the fact that we can describe something that we have no familiarity with as complete information of what's going on is truly baffling.
And I think that's what fascinates me the most about it is that I just have such a poor intuitive grasp of it. Again, right. I hear you saying these words, I can try to follow the equations, but it's just
on a human
That's
level, we're not
thing.
going to have intuitive grasp into these concepts.
Yeah.
That's why we call it a counterintuitive field of study.
yes.
That's why Feynman himself said that if someone says they understand quantum mechanics, they're lying.
Well, and I suppose that also makes it very difficult to easily explain quantum mechanics to somebody who isn't in your field because the field that you're in is less well understood, so there really aren't, masters. There aren't people who truly fully understand mostly everything, so it's going to be very difficult to break it down to a point where you can actually easily explain it because you have to start getting into the weeds really, really fast to even try to explain what's going on.
Yeah, that's kind of why I structured what I was talking about in the way I did.
Yeah.
I decided to go with common misconceptions just because of the fact that that's the easiest way to really rein in these topics. Because if we really get into the weeds, we really, really get into the weeds.
Oh, exactly, right. You at some level you can no longer just use analogy and you have to start cracking out equations, and that's where you're going to lose everybody.
Yeah, I didn't want to bust out good old Sakurai and just give you a lecture out of the
explain. So, Rob, can you please explain to me why physicists like to use a bunch of weird equation symbols?
You'll have to be more specific. I mean, notation is horrible. I'll give you that. Like using the Greek letter rho for 5 different things, it gives me a headache.
More like about the ego thing.
The ego thing. I mean, sure, we have complicated equations, and yeah, we have a lot of symbols, but I mean, I think at the end of the day, people just like the Greek symbols. I think also it's because of the fact that you don't want to write a bunch of equations using, like, Latin.
Yeah.